one of the greatest conservation stories in biology is the story of the whooping crane. They used to number 10,000 in the US, but by 1938 their numbers had dropped to only 15 individuals. So scientists had to figure out where are they breeding, how do we protect those areas, and you can see the population is starting to rebound. But the health of the population is dependent upon the size of the population. How do we increase the size of a population? Through births and immigration, new individuals coming into the population. Likewise, how do we decrease it? Through deaths and emigration. These things contribute to what's called the intrinsic growth rate. Is it increasing or is it decreasing? It's not the only characteristic. We also have the density and distribution. We have the sex ratio and the age structure as well. But what other factors outside of this intrinsic growth rate can affect their growth? Well, we break that into two groups, density dependent and independent. Density dependent factors are factors that limit growth based on the density of the population. So if you think about it, as the population's density increases, if there's not enough food or water or shelter, we call those limiting resources. And what happens to the population? It'll eventually level off. It hits something called a carrying capacity, or K. It's the maximum number of individuals an area can support. We also have density independent, and those are going to be things just related to chance. So a flood or a fire could be examples that limit the size of the population. So in population ecology, we're studying these factors, and scientists come up with models that help to describe what's going on in a population. So a famous model is the exponential growth model. What we're looking at is this growth rate and how it's increasing the population over time. And then we have a logistic model. It's also showing exponential growth, but eventually it's reaching what's called a carrying capacity, or this limit of population growth. And so the population size is incredibly important. So if we have these rabbits, so we have 9 rabbits, then their n value at this point would be 9. If we lose 2 of them, our n value is 7. If we gain 3, now our n value is going to be 10. It's the set number we have. But also density is important. That's the number of individuals we have in a given area. And so we could call this one density, but we would call this greater density. We could also look at their distribution. I would say that these rabbits are now randomly distributed, but they could be distributed uniformly, or they could just be clumped in their distribution. And we could also look at their sex ratio. So how many of our males and how many of them are going to be females. And we could expand that to look at what's called their age structure. Not only what is their gender, but also how old are they. So we could organize them like this, where this is going to be our first year female rabbit, second year, and third year, and we can do the same thing with males. But when it comes to the health, the population size is incredibly important. It's dictated by births, deaths, immigration, and emigration. And so we have a formula that allows us to look at that. And the calculations are very simple. You can do them just in your head. And so let's say we have a population of 10. So our n naught is going to be 10. That's our initial population. Here's our equation. So it's really simple. The change in n is going to be the births minus the deaths plus the immigration minus the emigration. So let's look at this population over here and see what happens. So this rabbit gave birth to 3 other rabbits. And so if we write this out, what's our births going to be? It's going to be 3. Now let's watch the population again. So you can see one of the rabbits died. And so we're going to put a 1 here in the deaths. We could look at immigration. How many come in? Looks like just 1. So we would put a 1 right here. And then how many emigrate? It looks like 2 left. And so we would put a 2 right here. And so the delta n, or the change in n, is simply going to be 3 minus 1 plus 1 minus 2, or 1. That's the change. Or we've seen an increase in 1. Now what's the growth rate? The growth rate is going to be the change divided by the initial population. So 1 divided by 10 gives us a 10% growth rate, or 0.1 is our growth rate. We call that the intrinsic growth rate. And as long as we have no other factors outside that population, that will remain constant over time. And you could solve a really hard problem. If we have 1 million people in an area, 100,000 are born, 10,000 die, if you're given the immigration and emigration, you should be able to calculate R for that population. So if we study a group of rabbits over time, their population will increase, but it'll eventually level out at some point. Now that leveling out point is called the carrying capacity, or the K. Now, why is a population going to level out? It's because they're running out of something. They're running out of food or water or shelter. And so we all call all of those things limiting resources. Disease could be another limiting resource. The more rabbits we have, the more disease, and so it's eventually going to level it off. Now, it won't look perfect like that. In a normal population, it's going to have overshoots and it's going to have a lot of die-off, but we're going to have that average that we eventually hit. These are density dependent factors because they're based on the density of the population. We can also have density independent. So imagine that these rabbits over on this side are killed in a forest fire. That's just chance. It's just chance taking over, and so it's not based on the density of rabbits that we have.